Okay, we are on FTC part 2 now, part 2. So we did part 1 for 1 day and a half maybe. And then the second day we did average value and mean value theorem. We're now on part 2. So I'm going to show you how part 2 comes about. First, let's just kind of talk about part 2. Part 2 says, if f is continuous on the open interval containing a, then for every x in the interval. Okay, so this is the important part. D dx of the integral from a to x f of t dt is equal to f of x. This is part 2, FTC. Mm-hmm. Okay, this is the important part. Derivative of the integral from a to x f of t dt. So notice that there's a variable change because I'm going to tell you why there's a variable change. The variable change is not a typo. There is a reason for that change. And then that whole thing becomes f of x. Okay.
Is that just a different function?
Yes. It's a different function.
The derivative of...
The integral. The derivative of the integral.
Okay,
Yes.
say like g of x. There's like for an example.
There is a reason we write f twice, which I'll show you next. So we want to keep it to the same f, not change it from f to g.
But it's the same function?
Yes and no. So it depends. So I'll show you. Yes.
Isn't the derivative of an integral just the same thing?
Yes.
So
That is what part 2 is trying to say. However, the application may be a little different depending on the problem. That's why I'm going to have to show you. Okay. Yes. Okay, proof. So again, I'm going to draw that same curve from before. This is f of t. Okay, this is t, not x. Okay, and the proof or the FTC part 2 says the integral from a to x. So that says basically I have an a here, and then I have an x here. Now x is not stationary. X is moving, or x can move, but a starts. It's a very definite point that starts. X can be anywhere. Okay, so we're trying to basically find this area, right? So once we do find that area, we would just say that area is going to be, remember FTC part 1? The integral from a to x f of t dt is equal to big F minus big f of a, right? Now what's going to happen is I'm going to take the derivative. So if I take the derivative of this whole thing, are you guys with me?
Yeah.
I'm taking the derivative of this whole thing with respect to x. Okay, so then if I take the derivative of this whole thing, then basically this first part becomes little f of x. The second part is a constant. It goes away. Yes? Huh? Okay, so when you take the integral of something, you have FTC part 1. So the area of this minus the area of that. When you take the derivative again, that integral, which is the area, becomes the original function, but with a variable switch. The second part is a constant, so when you take the derivative, it becomes 0. Okay, let's go ahead and look at an example. So essentially, what happens is when you take the derivative of an integral, it kind of just says when the two functions cancel each other. Because you're basically saying integral of a derivative. So you come back to where you were. Okay? And so then you can pretty much just make this assumption every single time. Your first number, if the lower limit is a constant, and the the upper limit is a variable. And then we want to make sure the variables are the same. If that happens, then you can just make a quick switch because it's just that. It's the same function with a variable switch.
That's the answer?
Yes.
Because we can.
Because when you take the derivative of a integral, all you're doing is changing the variable.
Okay.
Okay, so again, take the derivative of an integral, you switch just the variable if the lower part is a constant and the top part is just a variable. Okay? All right, so let's look at this practice. So we're going to take the derivative of g of x. So g prime of x is equal to what?
1 plus x squared.
Square root 1 plus x squared. Okay, when the lower limit is a number, the higher limit is just an x. Okay, this has to apply. It has to be lower limit of number, the higher limit of variable. If it's not, you got to do something else to find the answer. Okay, next one. Derivative of h of x.
Sin x over 1 plus x squared.
Yes, so it's just a direct switch. This is FTC part 2. Just keep that in mind. Okay, now another different example. What happens if we have this? This is not x anymore. This is x cubed. Okay, so,
Just plug x cubed into it.
Okay, that's a very good question. That's a very good suggestion. So when we take the derivative of this, it's the same idea. Again, the lower limit is a number, the higher limit is a variable. So we're just going to go and plug it in. However, it is not that simple. Yes, let me finish. Okay, so when we take the derivative of an integral, we just do a plug-in. However, the higher limit is not just an x, it's an x cubed. Therefore, we need to take the derivative of the top. So if it's not a direct substitution with an x, we have a chain rule. What is the derivative of x cubed?
3x squared.
So 3x squared is going to be part of my solution now. Okay, so please be careful of that. Next. All right, derivative of this one. Go ahead and give this a try. Okay, so the answer is secant x to the 4th times 4x cubed. That's it.
So the
That's what I did.
All right, let's have you guys try another one. Okay, the derivative, so you're going to take this and just plug it in. Okay, times the derivative of square root x, which is 1/2 x to the negative 1/2, or just, you can change that. Okay, this is going to be x over x squared plus 1 times 1 over 2 root x. Okay, the most simplified version of this is you need to cancel these two. So this becomes square root x over 2 times x squared plus 1. All right, now let's go ahead and apply. Yes?
The derivative of square root x.
Yes. Square root x is x to the 1/2.
Oh,
Okay, so now we're going to apply with a graph. Okay, so this graph shows you h of x, which is the integral from 0 to x squared of f of t dt. And you have this graph. Okay, so copy that down first, at least copy down the function first, and then we're going to use this graph to help us figure out the answer. The graph is actually really simple. The only thing that's labeled is the x-axis, right? So that means they really only care about the x-axis part and probably your increasing, decreasing part. All right, so now let's look at the question. First question, find the derivative of h. Find the derivative of h. Go ahead and try that. Okay, the derivative of an integral. All right, so the integral, okay, let me just rewrite this. F of x, h of x is the integral from 0 to x squared of f of t dt. So when we take the derivative, the lower limit is just a number. The higher limit is a variable. We're going to plug in f of x squared. We don't have a function. We don't know what the function is. Use the f of x. Okay, times the chain rule. So this is the answer. Okay? Next, this is the hard part. This is where you need to talk to your partner and try to figure this out. Find all values of x that h has a relative minimum. A lot of you missed this on the Monday special. Relative minimum, okay, I'm going to give you a hint. Relative minimum means what? What are you looking for?
Smallest one.
Derivative?
I mean like that.
Huh?
Equals 0.
Yes. Derivative equals 0. And then what? Yes, you have to use a sign chart to check. Is it really a minimum or is it actually a maximum? Okay, now remember your derivative is this one. Think about how that combined with that graph is going to help you figure out where the minimum is. Okay, keep your questions for later. You got to think through this. You can do this. So whenever you see this kind of questions, the first thing is like, oh my gosh, what am I supposed to do? You just go back to things you know. So relative minimum means the derivative is 0. Okay, so then you go back to the derivative and you say, okay, derivative is 0. That means there are only two things that can happen. Is you have two factors. It's either this is 0 or this is 0. So that means 2x is equal to 0, which means x is 0. Or fx squared is equal to 0. That requires you to look at the graph. So if you look at the graph, the question is, where is the graph 0? Well, the graph is 0 at 0, 5, and 10. So those are the 3 points. So x squared is equal to 0, 5, or 10, which tells you that x must equal 0, square root 5, or square root 10. Okay, next, you don't know whether it's going to be a maximum or minimum, so you got to check with your sign chart. So then you want to just plug it back into the derivative and check. So between 0 to square root 5, this graph is below. So, all right, good luck. This is going to give you a minus because the graph is below, right? And then this part is going to give you a positive because the graph is now increasing. Or above, sorry, above. And then, yeah, I think there's nothing after this because there's no more graph. So then this is decreasing, this is negative and then positive, so that tells you square root 5 is going to be the answer. So x equals square root 5 is relative minimum. Justify your answer. How do you justify?
Changes signs.
Because what changes signs?
The derivative.
H prime of x. H prime of x changes signs?
Changes from negative to
Yes, from negative to positive. Yes.
So it changes sign at 5 instead of.
It's x squared, not x.
Yes, they're asking you for H prime,
Oh, okay.
not F. Okay, so we're going to do more of these kind of problems to make you feel less panicky when you see something like this. But anytime you see something you've never seen before, go back to things you know and then just apply them. It's always going to be something you have learned.